All right, the next type of non-continuous basically is discontinuity. There's three types of functions that are discontinuous. You have infinite, which means it breaks. It's basically your vertical asymptote, which we'll get to later. But it's your vertical asymptote, and one side goes down to negative infinity and one side goes positive infinity, and they never connect. So that's an infinite discontinuity. The next one is there's a huge break in the graph. Those are your piecewise graphs. You won't see those very often, but if it's a piecewise, it's going to be a jump discontinuity. And then the last one is you're going to have something like completely perfect and you look like you can trace on it, but all of a sudden there's a hole, and we'll get to holes later. Remember vertical asymptotes and holes from last year. But there'll be a hole, and so you kind of have to skip one tiny little spot, but then the graph continues later on. So we're going to work out this one problem. Determine whether each function is continuous at the given x values. Justify using the continuity test. If discontinuous, identify the type of discontinuity as an infinite, jump, or removable. So what we're looking at is we're looking at f of x equals x minus 2 over x squared minus 4. So, and we're trying to figure out if it's discontinuous at negative 2 and positive 2. So we're going to do the first test that makes it obvious. Just plug it in. If I plug in 2, I get 2 minus 2 over 2 squared minus 4, and then I get 0 over 0, and you never can have 0 in the denominator. So already we can tell it's going to be discontinuous. So right now we're just going to work with the f of 2. So we do our table thing. So what we're doing is we're trying to find the limit of x approaches 2 of x minus 2 over x squared minus 4. So we're going to do the table of numbers. So here's your t-chart. Here's the 2. And this is really where the table of numbers is going to help you guys out. It's kind of silly to do the table of numbers when it's continuous, but if it's discontinuous, it makes sense because obviously we plugged in 2 and it's undefined. So right now, all we're trying to do is figure out if it's a jump, a removable, or an infinite. We know it's not a jump because it's not piecewise. So we're trying to figure out if it's removable or if it's discontinuous. So we go to plug in numbers. So we just think of numbers really close to 2 on the left and really close to 2 on the right. So we can say 1.99, 1.9. So those two numbers are really close. 2.01, 2.00, or I'm sorry, 2.1. So what we have to do is we have to plug in the numbers. So we got x minus 2 and x squared minus 4. And then we're saying right now 1.9 is plugging in for x. And we're getting 0.25. 2564. So now let's plug in 1.99. X. So we get should have made these bigger, 2506. That was 2.2504. So now we're going to do 2.01. And this side is 2493. And then we're going to do 2.1 for x. Two, 4, 3, 9. So what we have to decide here is obviously when we plugged it in, it didn't work. So it's discontinuous at 2. But what we're trying to find out is what is the limit as x approaches 2. Even though it's discontinuous, it sometimes will have an answer. So we look at as it's approaching 2, and we're looking at these values. Well, 2.5, 2.5, This side's a little lower than 2.5, so 2.4. So it's actually approaching 1/4. Even though we can't find the solution plugging it in, the actual answer is 1/4. And because it is approaching something, we can call this a removable discontinuity. It's a removable. So pretty easy there. So now what we're going to do is we're going to try with the -2. So let me get this. Same problem, but we're trying it at -2. So at 2, it's a removable. All right. So we have f of x equals x minus 2 over x squared minus 4. And we're trying now, this time is x equals -2. So first test this one is plug it in. F of -2 equals -2 minus 2 over 4 minus 4, which equals -4 over 0. So we already proved 0 is in the denominator. It is discontinuous. So now what we have to do is we have to figure out the limit. What is the limit as x approaches -2 of x minus 2 over x squared minus 4? So now we have to figure out the limit here. So we do our table. Okay, so here's -2. We know it doesn't work. We've already tested that. But we're going to do -2.001, -2.01, -1.999, -1.99. We're just trying to get really, really, really close to the value too. Also, you're going to have to remember your negative numbers are backwards because a lot of you guys are going to try switching it. So let's start plugging them in. -2.01 for x. And we get -100. -2.001 for x. And we get -1000. Okay, so now we're going to plug in -1.999 approaches x. We get positive 1000 and -1.99, plug it in, and we get 100. So now we need to look at the table of charts. Well, your left side is going negative, and your right side is positive. So because it's not approaching the same value, -1000 and 1000 is not approaching the same number, you can actually say the limit does not exist. And because it does not exist, it's an infinite discontinuity. So let's look at the difference between the two again. But first, just remind you, on the discontinuity, there's 3 types. Infinite means it's going in 2 totally different directions. It has a big old jump in the middle, the jump. Those are your piecewise. And then it's one graph and there's one tiny little spot removed, which is the hole. So the first one was the -2 one. We plugged it in, it didn't work, it's undefined. We did a table of numbers, we got really, really close to that number. We're showing it as it approaches it. And when we look at it, it's approaching 2 totally different numbers in the range. So since it's 2 different numbers in the range, which is your y value, it does not exist, and it's an infinite discontinuity. When we plugged in the 2, again, we got 0 in the denominator, it was undefined. So again, we've got numbers approaching it in the domain, or the x, so it's approaching it. And then when we plugged it all in, we're looking at it in the range, which is the y, and it's actually approaching the same number, which is 0.25, which is 1/4. So it's a removable. And so as the limit approaches 2, the answer is 1/4. All right, the next thing we're going to look at is called the intermediate value theorem. Doing the same thing, we're looking at the graph as it approaches stuff, but we're looking at it as it approaches at the zeros. So we're going to make this very basic. Here's the graph. So it's a determinant between which consecutive integers the real zeros of the function are located on the given interval. So by looking at the graph, these are your two zeros. So it's between -1 and 0 and 1 and 2. Those would be your consecutive integers. But that's just by looking at the graph. What we really want to do is we want to see it as algebraically. So we do a table of numbers. And what we can do is we can use the numbers. We can see it's about -1 to 2. So I would go -2, -1, 0, 1, 2. So -2, -1, 0, 1, and 2. So now what we do is we plug the values in. So let me get this in the calculator. Alright, so we're going to plug in -2. So -2 for x. And we get 5.25. Now we're going to plug -1 in. -1 for x. And we get 1.25. 0 for x. -0.75. 1 for x. We'll put -0.75 and 2 for x. 1.25. So when we look at the 2, we're looking at where it switches from a positive to a negative. So these two. So the two consecutive integers is it goes between -1 and 0. See it? And it goes from 1 and 2. You can do this by looking at the graph, but to check it algebraically is you just put all the integers in and you just figure out where it goes from a positive to a negative between the two. So we wouldn't do these two because it's two positives, and we wouldn't do these two because it's two negatives. All right, I know this lesson's really confusing. This lesson takes a little bit to get used to. So ask questions. The homework is page 30. It's 1 through 10 all and 13 through 21 odd.